does this toast taste better than this white bread slice? Or this golden brown dosa better than a homemade white dosa? Or this golden roasted potato better than this boiled mashed potato? Why is it that above a certain temperature, cooking seems to produce astonishingly amazing aromas and gorgeous brown color? The smell of coffee, chocolate, the unforgettable aroma of a bakery, grilled meat, or the brown spots on a chapati. Would it surprise you that it's all the same family of chemical reactions, named after a French chemist who had absolutely nothing to do with food? Louis-Camille Maillard was researching biological protein synthesis, meaning how our bodies make proteins. And he happened to notice that sometimes sugars and amino acids, which are the building blocks of proteins, reacted together to produce something brown. Ironically enough, his research would go on to have entirely different implications in the world outside food. Not very nice implications. But we will get to that later. For now, we're going to focus on delicious food. As any food scientist will tell you, all cooking is chemistry. But interestingly, till the temperature goes above the boiling point of water, most cooking involves no major chemical reactions. They are mostly physical changes. Let me explain. 1. Starches and carbohydrates absorb water and swell in size. No chemical changes. 2. Proteins denature, meaning that they lose their three-dimensional structure and become harder. Still, no chemical changes. A few proteins like enzymes stop functioning because of this, even if their chemical formula still remains the same. This is important in cooking because it prevents food from going bad quickly after being cooked. 3. Fats don't change at all. In fact, they remain fats till they get to your small intestine. But once the temperature reaches 140 Celsius, interesting things start to happen to your food. At this temperature, most surface moisture would have evaporated. Then a dance of sugar and protein begins. Melanoidins are responsible for the brown color in various foods. Pyrazines contribute roasted, nutty, and toasted aromas. Thiazoles offer roasted and meaty aromas. Furans impart a caramel-like sweet and fruity aroma. Aldehydes give a variety of aromas, ranging from green and grassy to nutty and fruity. Ketones contribute to buttery and creamy aromas. Oxazoles provide meaty and savory aromas. And this goes on till about 170 Celsius, after which, the longer you cook at these high temperatures, some of the byproducts of this reaction are not good for you. For example, 1. Acrylabide, which is typically produced when you cook carbohydrates like very brown French fries. While our bodies can deal with the kind of amounts you are likely to produce in a home kitchen, very regular consumption of starchy, deep-fried foods comes with this risk. 2. Heterocyclic amines and polycyclic aromatic hydrocarbons, typically produced when you grill, fry, and barbecue meat at high temperatures, and also found in a place you will just not believe, but you'll have to wait and watch till the end of the video to find out. 3. Advanced glycation end products, AGEs. Sugars, fats, and protein can react at very high temperatures to produce molecules that have been linked with everything from diabetes to heart disease to Alzheimer's. So again, grilled and fried food, consume in moderation. Also, your own body produces AGEs, but more on that later. So let's leave this boring theory aside and let's get practical. How do you master the Maillard reaction in your home kitchen to make food insanely delicious? 3 words: brown is beautiful. Let's start with dry dishes. If you are making a dry dish, this is straightforward. There is already less water in the dish, and as soon as most surface water evaporates from your ingredients, they will start to brown. You want it golden brown, but not too dark brown. at which point things become both bitter and unhealthy. So how do we maximize browning in a dry potato dish? There are few dishes more addictively delicious than a perfectly golden roasted potato. A potato is mostly water and is made of two kinds of starch, amylose and amylopectin. When you soak potatoes, some of the loose amylopectin washes off. And this is good because it will prevent the potato from sticking to each other in the pan. Of course, you can now simply saute the potatoes in oil, and once you add salt, that will further dehydrate the surface of the potato and you will get pretty decent browning. But Maillard reaction ninjas use another trick to make this process even more amazing. Parboil the potatoes with a tiny pinch of baking soda. Plants contain pectin, a kind of soluble fiber in their cell walls. And in acidic, meaning low pH conditions, it forms a gel. And we are familiar with this texture because that's how jams work. Pectin in fruits, which tend to be slightly acidic, sets into a jammy texture. But baking soda is alkaline, and that prevents the pectin from setting when you cook the potato. And thus, the surface of the potato now ends up having more grooves, and thus more surface area. In cooking, surface area is a very useful concept to understand. More surface area equals faster evaporation of water from the surface. This is how a puri deep fries. It loses moisture from its surface and the gluten traps the water that turned into steam inside the puri, causing it to puff up. Now, a parboiled potato with a small pinch of baking soda, don't add too much or your potatoes will turn into mush, end up having more surface area. So now, if you saute these potatoes in oil, they will crisp and brown even more effectively. The sugars in the starches of the potato will react with the amino acids in the proteins in the potato, and the Maillard magic will happen. Baking soda also has the superhero feature of accelerating the Maillard reaction. This is a trick you can use when making pakoras, bhajiyas. When you make the batter with besan, adding a pinch of baking soda before you fry will get you even more even browning. Now let's discuss gravy dishes. If you are making a gravy dish, then you can use all the tips you just learned and do what restaurants tend to do. Brown the main ingredients before adding them to your gravy. Let's take aloo gobi as an example. Steam the aloo and gobi and then brown them in a little oil before adding to your gravy. By the way, restaurants simply just deep fry all ingredients fully in oil. Chicken or meat dishes, grill the meat before adding to the gravy. But the most impactful daily use of the Maillard reaction in the Indian kitchen is browning onions. As most of you will agree, it is slightly frustrating. Onions are 90% water and take forever to become brown. And the second they do, they start charring and become black and bitter in a very short amount of time. Properly caramelized onions take a lot of time we usually do not have. So you can use the kitchen superhero again, baking soda. A very tiny pinch will get your onions brown in half the time that it takes otherwise. But it will also make it slightly softer and mushy. So you take your pick. So the key food science tips to master the Maillard reaction so far: number 1, increase surface area. Number 2, reduce surface water. You can dry stuff before cooking or adding salt to dehydrate faster. And 3, increase pH. Add baking soda. The Maillard reaction is everywhere. It's what makes delicious brown spots on your chapati, the aromatic brown crust on a bread. In fact, the addictive smell of a bakery, the aroma of coffee, chocolate, grilled meat are all thanks to the Maillard reaction. But it doesn't end there. And that's where we go right back to the start, where I mentioned that Louis Camille Maillard original research also had implications in areas other than food, and not very nice ones. Turns out that the Maillard reaction is not just something that happens in your frying pan to make food delicious. It also happens slowly inside our bodies as we age. It happens slowly over time because the temperature of our body is 37, not the 140 Celsius in our frying pans. For example, in our skin, when sugars in our body chemically react with proteins in our muscle tissue, producing what are called advanced glycation end products, AGEs. These AGEs accumulate over time and can make the collagen and elastin in our skin less elastic, which leads to wrinkles and sagging skin. It is a bit like how a perfectly soft and flexible piece of bread turns rigid and brown when toasted, much like our skin over time. Similarly, in the lenses of our eyes, sugars can react with the proteins in similar ways. Over time, this can lead to the lens becoming more rigid and less transparent, which can contribute to the development of conditions like cataracts. People with diabetes who tend to have higher levels of sugar in their blood can see an accelerated formation of AGEs. Now you know why it's generally considered a good idea to not keep blood sugar levels high regularly. But remember, the Maillard reaction in your kitchen has nothing to do with the Maillard reaction happening inside your body. So I want to end this video on a more positive note. Remember, I told you about one of the byproducts of the Maillard reaction that is produced when you grill food at high temperatures. They're called polycyclic aromatic hydrocarbons. And I told you that you just won't believe where else we can find them. Turns out they are found in interstellar dust and are said to be products of the Maillard reaction, formed at the ultra-low temperatures of space over billions of years. And it is believed that when that dust condensed to form stars and planets, these molecules, the polycyclic aromatic hydrocarbons, could very well have been one of the key building blocks of life on Earth. So when I eat this browned piece of toast, which according to a lot of scaremongers here is poison, me, a human being, aging by the effects of the Maillard reaction, is eating an originally tasteless product of a cereal grain made delicious by the Maillard reaction in an oven on a planet where my own existence was made possible by molecules in interstellar dust undergoing the same Maillard reaction billions of years ago.